Okay, so our first unit is on something called momentum and impulse. And ideally, you guys should remember a little bit from Physics 20. We would have done a unit, and maybe I taught you, maybe Ray taught you, maybe somebody else taught you, but we should have done a unit where we talked about how things move. Unit 1 in Physics 20 is kinematics. It kind of describes the motion of things as they're in motion. You should have learned kinematics equation involving velocity, distance, time, acceleration. But the second unit would have been on dynamics, and we would have talked about how things get into motion. And there were 3 laws of motion you should have learned that were Newton's 3 laws of motion. Does that ring a bell at all? Okay, let's see how well you remember things. Does anyone recall Newton's first law of motion? You got it. That's it. Yeah, and could you define inertia a little bit more than just the word, though? That'll work. Or things that rest stay at rest. Yeah. So if you didn't catch that, Newton's first law is things that are moving tend to stay moving unless something stops them. Things that rest don't just randomly start moving, right? There's a t-shirt over there by the side wall. I don't expect it to start moving, right? Whereas the Earth is constantly moving around the sun right now, I don't expect it to stop. Inertia keeps things moving. Okay, so that's Newton's first law. Newton's second law, anyone happen to recall that at all? Well done. Yeah, so the heavier it is, the harder it is to accelerate. And Newton's second law is actually a formula that hopefully you're somewhat familiar with. It is that the net of all your forces is equal to mass times acceleration, meaning that if you have a higher amount of mass, it means that it decreases how much you can accelerate it. Simple little example, but like I went camping this summer and I have a half ton. It's very easy for me to pull my truck with nothing in the back, right? Put a camper on the back, right? And all of a sudden now when I'm trying to accelerate, do I go to 0 to 60 quite as fast? Well, no, right? Because the increase in mass drops your acceleration. Okay. Anyone recall Newton's third law of motion? Yeah, everything has an equal and opposite reaction. So if I push myself forward by jumping, I actually push the Earth backwards. I know that seems kind of dumb, but everything has an equal opposite reaction. Okay. We're going to extrapolate on those 3 laws of motion in this unit here on momentum and impulse. But we're really going to specifically focus on the concept of collisions. Okay, that's what we're going to extrapolate from. We're going to talk about those 3 laws of motion and how things run into each other and hit each other. And you're probably already familiar with the word momentum because like we use it in everyday life scenarios. So let's get started here. My first slide, you guys can like read the words on there. I hate reading off the slides. I mean, there's some words on there I've already discussed. Hopefully you know the idea of inertia. Inertia is about Newton's first law. Objects continue to move. Well, if we don't use the word inertia, a synonym for it is often the word momentum. Momentum is a very similar concept to Newton's first law. It's a way of calculating its inertia. We're actually going to put like a numerical value on it, right? So if we have something that is not moving, its inertia would be 0. If we have something that's moving a little bit, it might have an inertia of 1 or 2. And if it's moving a lot and you need to try to stop something, like imagine that you're a vehicle and that you can't stop because it's icy roads, right? And you want to try to stop and you can't. Well, your momentum might carry a vehicle through an icy intersection. It's really the same concept as inertia. The only difference is this is our attempt at trying to quantify something. You guys familiar with the word quantify or quantity? We're going to put a number to it. That's all. Okay? It's kind of a hybrid between the inertia and the kinetic energy. Does anyone remember the formula for kinetic energy by chance? Kinetic energy is, because there's really 2 things that affect how much energy you have. How heavy you are and how fast you're moving. Imagine that you need to try to stop a vehicle that's, really, 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 really heavy and it's got to slam on the brakes at the last minute. Is it going to be easy to do that? Well, no, because it's so heavy. Or imagine that you're traveling 100 kilometers an hour on the highway. Is it going to be easy for you to stop in the blink of an eye? Well, no, because your velocity is high. So really, those are the 2 variables that we've talked about before in terms of energy. Well, the formula that we have in terms of momentum is this. P equals mv. It's our first formula we're going to learn this unit. P is the unit we use for momentum. Here, I'll stand here so I'm not in your way. P is the momentum unit. At some point, we ran out of letters. Why can't we use m for momentum? M is used for mass, right? And we're going to discover that a lot as we go through this course, is that like there's only 26 letters in the alphabet, and at some point we run out. So P is momentum, and I got a couple little notes on here. It has units of kilograms meters per second. It does not get like a special unit like a Newton or a joule. You guys remember some of those units? It literally is the units of mass and velocity. Mass is measured in kilograms. Velocity is measured in meters per second. That's its units. Now, it's similar to energy. It takes energy to stop something that's in motion. It takes energy to get something moving. But read this line here. Unlike energy, which is a scalar, you guys remember scalar, where like direction doesn't really matter? Momentum is a vector, because we need to care which direction you're giving an oomph to. And I think that's the best word I can give for what is momentum. It's the oomph that something has. The more power behind it, that's not really the right word though, but like the more I hit something, the more momentum I'm trying to give something. And so therefore direction matters. Because what if I throw something left versus right versus up versus down? Wouldn't direction make a difference in things? I skipped over a slide for any of you guys who are following along online with my notes. This is actually an animated version of what was in my notes otherwise. You're probably familiar with this thing. It's called a Newton's cradle. This is just the animation, so it works. You ever see these on like, someone's desk? It's like one of those knickknacks that someone might have in like an office building. You guys know what I'm talking about here? This is called the Newton's cradle. All right. And if you haven't seen this before, the basic idea is that as this ball comes down and hits this one right here, that inertia, or the word we're now going to use is momentum, is going to be transferred from one ball through all the other ones to the last one. Watch, right? This one hits that one, which hits that one, which hits that one, right? And I can't even say it fast enough. And it kicks the one out the other side. This guy has some momentum. Its momentum hits that to that to that to that and kicks the one out the other side. And that's a good visual way of seeing momentum transferring, which is why the main focal point of this unit is all about collisions. Anything that crashes from one object to another, that's what we want to focus on. And that's really, in essence, what this Newton's cradle is a whole bunch of collisions happening back and forth. So there's basically then two ways that you can have momentum. You can either have something that's really heavy, because mass is part of its equation, like say a bowling ball. All right, imagine that you were to be standing in a bowling lane and someone were to roll a bowling ball towards your shin. I wouldn't be thrilled about that, right? It may not be going fast, but the bowling ball is so darn heavy that when we calculate how much impact, or momentum as the word we use is, if you increase the amount of mass in the object, the more it's going to hurt, right? Or take Mariano Rivera throwing a fastball, right? Is the baseball itself all that heavy? Well, no, it's like 195 grams or something like that. But he's throwing it 100 miles an hour. It's going to leave a bruise, right? So really, those are the two things that you can do to increase your momentum. And I know, if you're in my physics class last year, you know the words for relationships. For those of you who maybe aren't familiar, I need to introduce, or at least remind you if you don't know, there's two types of relationships you should know. One is known as a linear relationship. Does that ring a bell for some of you guys? And another one is known as a inverse relationship. Does that ring a bell at all? If I were to draw a graph of a linear relationship, it would mean that your momentum based on mass would look like this. If you increased your mass, you'd have more momentum. It's like a straight line graph. An inverse relationship would be one of the graphs that kind of goes like this, which is where if you increase something, something else goes down. If I spend more time playing video games, I get less sleep. That's an inverse relationship. The linear relationships are if I increase this thing, this one also increases. So where I'm getting at here, if you're not familiar with the term, is that if I were to increase either the mass or the velocity, there is a direct linear relationship between these objects right here. The worst thing that can happen, though, is what if you're trying to have something that has both a large mass and a large velocity? I'm guessing this is a photoshopped image, but it looks so cool, right? I mean, it's actually one of the reasons why car crashes are so devastating. Sometimes people are like, oh, I was only traveling 50 or I was only traveling 30, and they still got whiplash. Okay. I've got a friend who got into a rear-end car accident. The car was only going 30 kilometers an hour. It wasn't all that fast. But the car that hit him was a big truck. got huge whiplash and has neck problems, right? And you think, 30, I can bike that fast. I go through a school zone that fast. When you have car accidents, maybe not a train mashing a car, right? But when you have cars getting into accidents, you often have large masses, large velocities. It means you have a huge amount of momentum. Because not only is the momentum increased by the higher mass, it's doubly increased by the higher velocity. Anyone ever travel in BC? Familiar with these ideas of runaway lanes? I am, because that's where I grew up. The idea here basically is that if you're going down a really, really steep hill, what if your brakes fail? Hypothetically, right? Well, Newton's first law of motion says objects in motion keep moving, right? And if your brakes are failing as you're trying to go down this hill, what's going to happen? You're just going to go faster and faster and faster, right? And eventually there'll be a bend in the road and you won't be able to make that. Really big problem on semis and big trucks, because if they've got a massive load, because they're huge, right? And they're traveling 100 kilometers an hour, if they can't stop, they need a backup option. So that's more or less what these things are right here, is that hopefully you can steer yourself into the runway lane in some sort of way to help prevent an accident. So, any questions so far on like the concept behind what momentum is like? Okay, let's try some calculations then. So before we get to that, I got to show you one more formula. There's two formulas we're going to learn today. The first one was P equals mv, which is your basic momentum formula. The second formula is actually somewhat based on Newton's second law. Do you guys remember Newton's second law? We wrote it out earlier. F net equals ma. That's Newton's second law. But if you're familiar with acceleration, you can actually remove the acceleration portion of the formula. So I'm just going to delete out acceleration, because what's another formula for acceleration? Velocity divided by time. Everybody catch that? And I'm going to do one more thing. I'm then going to take the time that's now on the bottom of this side of the equation. I'm going to times it up over to like the other side, the numerator of the other side. And we've made ourselves a new formula. The formula being force times a change in time is equal to mass times a change in velocity. And what's kind of weird about this now is that isn't mass times a velocity? Isn't that what we just said was a momentum? So we've really found a way to interweave a whole bunch of different formulas together now. We took Newton's second law, F equals ma. That's a formula we might be asked to use. P equals mv is a formula you may be asked to use. And this formula right here is kind of what happens if you like mush them together into like one big super formula. So the good news is this is a pretty low level kind of formula to work with. Generally there's 1, 2, 3, 4 variables. We usually give you 3 out of the 4. Say solve for the 4th. So, oh, I missed one thing before I move on. You know how we've been talking about that oomph that momentum has? There's actually like a technical word for it. We call it impulse. Impulse is like how long a force applies per time. If I were to hit the whiteboard like this, or if I were to really hit the whiteboard, I used more force the second time. It means I used more impulse. So like impulse is basically the amount of force you have and how long you apply it for. Imagine in your car you need to brake and you just gently hit the brakes. Low impulse. But let's say that you hit those brakes gently for like 5 hours. Well, that means you've actually used quite a bit of friction between the braking pads. Right? Whereas let's say that you stomp on the brakes. Well, now you're using lots of force. The word we use then is impulse. That kind of describes how much oomph you have in starting something up or in slowing something down. Okay, so let's try some math equations now. Some basic ones. Question 1. Let's say that a 1,000 kilogram car is going 10 kilometers an hour. So not all that fast. How much momentum does the car have? I don't want to be like cruel and come off as being mean on day one here, but this is about as entry level as it gets. I'm giving you momentum is mass times velocity, and literally I'm telling you the mass, I'm telling you the velocity. Plug it in a formula, but the answer is not 10,000. Why is the answer not 10 by 1,000? Units. Yeah, I hear a lot of you guys saying we have the wrong units. What's wrong with kilometers an hour? The standard units that we use are meters per second.
Grade 9 or grade 12 that have not had their picture taken, this is the Learning Commons to have that done. Again, any grade 9s or grade 12s that have not had their picture taken, please go to the Learning Commons. Thank you.
Okay, so if you didn't catch that, we got to convert the kilometers an hour to meters per second because the standard unit in momentum is in meters per second. So does anyone remember the quick rule for converting meters per second, kilometers an hour? Yeah, it's either times or divide by 3.6. All you got to do is just know which way you're moving here. So kilometers an hour is a much higher unit than meters per second. As a rough number, if you're going 100 kilometers an hour, it's about 27 meters per second. So if we want to drop this into meters per second, we need to divide this by 3.6. So 10 divided by 3.6 gives me 2.7 repeating. So that means my velocity is 2.7 repeating. Our mass is now 1,000. Multiply them by each other, you get 2777 kilogram meters per second, and that still is technically not really right because I'm still making mistakes on purpose. What am I doing wrong? Sig digs, yeah. Based on the significant digits we have, this has been recorded. The best I can say is it's got 4 digits of precision, but I mean, it may even only have 1 sig dig. This guy right here may only have 1 sig dig, but it's probably 2. So best case scenario, I might be able to say that this was recorded to the nearest whole number, so I should get 2 sig digs. So you probably need to write it more like this: 2.8 times 10 to the 3 kilogram meters per second. And I would change it to scientific notation here. If you're not familiar with that E that's right there, E stands for times 10 to the power of something. It's just the shorthand version of writing out exponents. If you're not familiar with that, can you let me know afterwards? One thing we're going to discover is that because I taught some of you and I didn't teach others, I'm going to kind of assume things once in a while that, like, you're familiar with that. If that, like, can you stop me, please? Any questions so far? That was pretty easy. Let's try another one. Let's say you have a 15 gram box. Pay attention to the units here. 15 gram box slides across the table at a speed of 4.6 meters per second. But it gets slowed down. Why is it slowing down, probably? I don't know. Probably friction, but maybe somebody hit it. I don't know. It really doesn't matter what it was that stopped it, but an impulse. I spelled that wrong, by the way. There must have been an impulse, because an impulse is like hitting something. It's speeding it up. It's slowing it down, right? An impulse is any word that changes the momentum of an object. So something slowed it down. We would like to calculate the impulse. What's impulse again? Well, impulse is just a fancy word for momentum. Okay? Impulse and momentum are kind of the same thing, and it's kind of the same thing as inertia. I know it's a pain in the butt that I've got 3 words that all kind of mean the same thing, but momentum basically is impulse, which basically is inertia. And if I could give like a word to describe it to my 7-year-old, I would call it oomph. That's what I would describe inertia as. How much oomph does something have? So what I'm really asking you to do is calculate how much momentum there is. Exact same thing. Only this time around we were asked to calculate mass times velocity. Same thing as before, but which velocity do I use? The change in velocity. Well done. If you didn't catch that on a previous slide here, I didn't point it out, but there's that little delta symbol right here. What if we don't stop something entirely? Right? Like, what if we only slow it down? Well, we only get credit for the velocity that was actually impacted. So when we do this question right here, if it went from 4.6 down to 1.6, the velocity change was actually 3.0 meters per second. Right? Use the change in the velocity when you calculate the impulse / momentum. Great question here. We can make it negative if we like. My suggestion always to you guys when it comes to using positives and negatives is ignore them until the end of the question. Remember doing that in like kinematics? Where it's like if it's going up, maybe make gravity negative, but if it's already going down, make gravity negative. Like just use your common sense on that. But you make a good point. When we're done, maybe if we have a negative number for my momentum, that makes sense. The negative is because we're slowing it down. Right? If we have a positive impulse, it means we're probably speeding it up. I can't just times by 15 though, right? You guys are all good with that because it's in 15 grams. The unit we need it to be in is in kilograms, so let's make it 0.015. So multiply those real quick. 0.015 times by 3. We get 2 sig digs, so I think I can leave it like this. I got 0.045. Anybody else get that? Tried it? Sweet. Okay. So again, I don't think that one's an overly challenging question yet because I'm literally just using the same darn formula. There is a vector arrow on top of momentum. So kind of like Drake was pointing out, we may need to, in a question, identify whether we're slowing down or speeding up and just use common sense. If it's going from 4.6 to 1.6, it's slowing down. So negative, I guess, makes sense. Questions before I move on? Okay, let's try another one. There's a rifle. And there's an 8.75 gram bullet inside a rifle, and it's going to exit the barrel of the rifle at 225 meters per second, ridiculously fast. It only takes a fraction of a second for the bullet to move through the chamber. My question now is how much force is there acting on the bullet? This is ultimately our question. How much force is there? Well, this is why I began our lesson with reviewing Newton's laws, because at its core, we're really being asked the formula F equals ma. The amount of force that we get is going to be mass times acceleration. But do we have acceleration information? Well, not really, but kind of. Well, if we use the modified version, where we change out acceleration for velocity over time, throw time over here, maybe this formula is a preferable one to use. I have formula sheets, by the way, for anybody who wants one. If you guys were in my class last year, it's the same one still. So if anybody would like to have the same formula sheet you had in my class last year, feel free. It's the same one for 20 as for 30. It's on Moodle though, so if you want to save a sheet of paper. Anyways, this is what's on the formula sheet. So I mean, it's kind of silly that I did all of this work to go to this formula. If I want to isolate for force, algebraically divide both sides by time. And here's my formula. Force is equal to mass times by a velocity change, divided by change in time. Isn't the velocity over the time acceleration anyways? So, plug in some numbers. Let's see, what was my mass again? 8.75, I'll have to convert that. So it'll be 0.00875, there's my mass. My change in velocity, it kind of implies that the bullet was shot, right? What would the initial velocity of the bullet be? Probably 0. And once it's done accelerating, it was up to 225. And all of that happened in 3 to the minus 2. Let's grab a calculator. I got 65.625. Anybody else try it? 65.625? Okay. So verbally, I'll just write it out real quick here. I got 65.625. But don't mess up sig digs. When we eventually do a diploma, which is months away, please don't focus on that right now. But there's nothing worse than getting a question wrong on the diploma because you messed up sig digs. So looking back at the original stem here, it looks like this guy's got 3, this guy's got 3, this guy's got 3. So looks like it's 62.6 unit for force. Newtons. Cool. That's a 6, by the way. That's really gross. Let me fix that. We'll do it nicer. Okay. Questions so far? How am I doing? Did I say that wrong? Correct. Thank you. Sorry. That's a 5. Anyways, you get the point. Don't screw it up. Are you okay? Okay. Okay. Now, one of the things I need to point out, since I talked about a diploma a little while back, I may as well start talking about it now. For those of you guys who came from Physics 20, hopefully you'd agree that there was a lot of math calculations in Physics 20, right? Like that was a large part of what we did, huge math component. More than half of the Physics 30 curriculum, just so you're aware up front, more than half does not involve calculations. Okay? Physics 20, highly math-based. Physics 30, actually, very, very low emphasis on math, believe it or not. Most of it is about theory and understanding big picture concepts. And I don't know, I don't want to come off as making it seem like that was supposed to be easy, but I hope that the first 3 examples we did there, you're like, yeah, that's more or less what Physics 20 was, right? I give you a formula, you plug some numbers in a formula, you crunch out an answer, you do sig digs, you do units, you don't make any mental mistakes like screwing up a 5 for a 2, and like you get an answer, right? That's actually a very, very low amount of what we do in Physics 30. Most of Physics 30 is about theory. So I'm going to spend some time on the next few slides here discussing like the little intricacies of like what does this mean for real world applications of impulse. And I want to give an example here. Here's a theory type question. Why does an egg crack when it hits concrete, but if I were to drop that same egg on a bed of straw, why does it make it? Anybody ever play Assassin's Creed video game? I don't know that one, but I was thinking Assassin's Creed because the one guy jumps off the really tall buildings into the pile of hay usually. Anyone know what I'm talking about there? You've seen those ones? Why does landing on a big, soft, spongy, cushy surface, why is that better than landing on concrete? Well, I mean, if you ask my 7-year-old, they understand it, but like I think their answer is limited to, well, because it's spongy. Right? Like if I go take my kids to the climbing wall, we took them bouldering, they intuitively understand, hey, a mat underneath is probably better to land on because it's cushiony. Right? But from a physics point of view, what does that change? Let's talk about why. The momentum that you need to stop is not going to change regardless. This momentum that you have, imagine you have an egg that's up here. It has a mass. If the mass hits the concrete or the straw, does the mass change at all? Okay, mass is a fixed variable. I can't fix that. What about the velocity the instant the egg hits the ground? Can I really change that either? Well, no, because, I mean, here it's maybe hitting the ground a slight fraction earlier than right here because it's slightly higher up. But at the end of the day, aren't both these eggs hitting the ground with the exact same velocity? Right. So in a way, what that means is that the momentum with which they're going to hit the ground, but we can now use another word, we can say the impact, the impulse, the inertia at which they're going to hit the ground, that's constant. But what I can change is force and time, because force is what breaks the egg. It's not the momentum that breaks the egg. The momentum causes force, but it's force that actually causes the egg to break. And this is where you need to know those relationships. What is the relationship between force and time? It's actually an inverse relationship. It's one of those indirect ones. I don't know that you guys are familiar, hopefully, with this sort of graph, but what ends up happening is if you increase the amount of force you have, it must be because you decrease the amount of time you have. And that's the reason why landing the egg on the bed of straw works better. Because what it's doing is it's increasing the amount of time the collision takes. The collision is happening anyways, right? The egg has to go from 5 meters a second to 0. It can't change that. But if it has to happen in 1 second or 2 seconds, I'd rather have 2 seconds. Why do we have airbags in our cars? To slow down the crash, right? I mean, it's also to prevent you from going through your windshield. But if you are driving in your vehicle and all of a sudden, Lord forbid, you happen to run into, I don't know, a big brick wall, you're going from 30 kilometers an hour to 0 in the blink of an eye. But if we have a big cushion in the front seat of your window, it might help slow you down just a little bit, with the idea being that if you can increase the amount of time a collision takes, it actually decreases the amount of force. Does that concept make sense a little bit? There's an inverse relationship there. It's actually one of the reasons why so many of our sporting equipments involve having cushioning. It's why we have these crumple zones in the front of cars. New cars are designed to crumple for safety purposes, because what it does is it slows down the reaction. It takes longer for the front end of this beetle here to collapse upon itself, and by slowing down, it therefore basically takes that exact same formula I just mentioned there. Momentum is equal to force times time. Why don't we isolate this formula for time, or sorry, for force? If I isolate this formula for force, it's momentum divided by time. Can I change the momentum change? No. Its mass is not going to change. The velocity it has to stop from won't change. What we effectively have then is the formula 1 divided by x. You guys are familiar with the formula 1 over x from math class? It's an indirect relationship. It's a reciprocal, meaning that if you increase the amount of time you have, it actually makes this whole number, it makes this whole number right here become smaller, and therefore drops the amount of force. Okay. Here's another picture of vehicles undergoing crumple zones. New vehicles are manufactured so that you have a nice high-strength iron frame around it, but like the back end and the front end of the vehicle are supposed to just like absolutely crush like a tin can. I mentioned my friend who got into a car accident getting rear-ended. His car is one of the newer type cars, and it wasn't really that much of a car accident. Like just the back end of his car completely crumpled, but like they had to completely write it off. But it was designed to do that. If you guys have seen vehicles from like the 1980s, my first car was a 1984 Buick Skylark. 1984 Buick Skylark. You gotta look it up. It was a boat. Like Buicks were known for being these just big, massive vehicles. But they're actually really safe because the trunk was massively long, the front end of the car was really long, and so it meant that if you ever got into an accident, there was a lot of distance that things could crumple. One of the most dangerous vehicles you could drive? Smart car. I mean, great for fuel, don't get me wrong. But if someone gets into an accident into a smart car, there's no compression zones available to help decrease the amount of force that car is undergoing. So anyway, it's not that I'm knocking smart cars. But... Okay, so let's try another math example that is kind of referencing this concept here. I have two examples back to back here, but we're going to change something here. Here you have a 75 kilogram man in a car accident traveling 65 kilometers an hour, hits a brick wall, there's no airbag, seatbelt catches him because the seatbelt locks, and he has to stop in like 50 milliseconds. Second scenario, there's an airbag. And the change now is that it took 0.34 seconds to come to rest, just because there's a little bit of cushioning for you to come into. Here's what I want you guys to try. I'm going to pause for a bit and have you guys try this. Use the formula F delta T equals M delta V. I'd like for you to isolate for force and do it twice. The only difference is one time you're going to use a time of 50 milliseconds. The other time you're going to use a time of 0.34 seconds. And I want to figure out how much difference in force there would be just by adding an airbag. And we'll see that that amount of force is hopefully life-saving. Is that fair? So why don't I give you guys a couple minutes here. Try this without me doing it first. See whether you can beat me to it. Oh, I should leave that up top there because some of you are looking off this, aren't you? Hey, buddy. Sweet. Oh, you're the best. It's hot in here. Oh, you're the best. I'm putting them in front of these cold air vents right here. No. I'm hot. I don't know. Is it hot in here? Yeah, like I'm... No, I know. It is what it is. It is what it is. But maybe it's something better than we have. Okay. Hopefully that was enough time for you to try this. Hopefully you can follow along with what I did on the board here. I'm just need someone to help me with the answers because I'm going to skip my calculator. Hopefully you follow this. 76, that's 75. Come on, Chris. 75 was the guy's mass, right? That never changed. 65 was the velocity. Why am I dividing by 3.6? Yeah, we want meters per second. Okay, so that never changed. The first time you do it, do 0.050 and divide by that. And then just to kind of save time, I wrote or divide by 0.34. So, did anybody do both calculations? Does anyone have the numbers? Can I write down like F1 and F2 perhaps? What did you get the first time you did a force? Anybody? 27. Okay, we'll call it 27,000 newtons. Second time? 3,900. Give or take. Anybody else get those numbers? I'm just trusting Carson. How much of a factor is that better than? I mean, just rough math. This is 27. This is like 3. It's like, what, 8 times better? Okay, this is a little off. 6.7 times better just by having an airbag, right? And I mean, how much did we slow down the airbag? It's still a third of a second. It's not like it took 5 seconds to slow you down, right? But rather than it being a fraction of a second, milliseconds, made a huge difference, 6 times better. So, does that make sense? Is that something you guys can replicate, hopefully? Hopefully you understand the theory. Because if I can point something out, as we're going through the course, don't just focus on the math. It is not the majority of what we do. Math calculations will be something you have to accomplish, but you have to understand the concepts. So, okay, last thing, then we're done for the day. I also need you guys to know about how to do graphs. I can't speak for those of you guys who had Ray, but graphing is something that hopefully you did a little bit in Physics 20. I know for you guys that I taught, we should have done a lot of this. Here is a really typical graph. Okay, this is a force times time graph. And we didn't do any of these in Physics 20, but what's happening with the amount of force right here over time? It's being held pretty constant, right? So that would be like me leaning against the wall right now. This would be a graph of what I'm doing right now. I'm applying a force over time, and the force is the same force it always is. Does that make sense? This would be like you're driving in your vehicle and you constantly have your foot on the gas. Okay. Well, we can actually use math and graphs together again. 2 of the things that hopefully you learned last year were that if you ever have a graph, and the graph is like a curved line like this, if you ever found the slope of that graph, the slope is always equal to your rise over your run. And so it's always equal to like A divided by B. I don't know what these 2 things are right here, but if A divided by B means something, it's your slope. Hopefully that rings a bell. Another thing you hopefully learned is that if you still have that same graph A and B, and I'll make it a triangle again just because, if you ever find the area of boxes underneath it using shapes, we call that like let's call it area. The area in this example would be whatever A times by B is. And so if you ever have 2 things that are multiplied by each other, if you multiply the 2 axes by each other, in this case it would have to be 1/2 base height because it's a triangle, but area can sometimes be useful to us. Look back at this. On one axis we have force and time. Well, does force divided by time give us anything useful? Not really. I haven't learned any formulas involving force divided by time. What about force multiplied by time, though? Is that a useful unit? Yeah, because what's force times by time equal to? Momentum. Or impulse, or impact, or oomph, or whatever it is you want to call it. So if I give you a graph like this, you should be able to calculate how much momentum there is just by reading the graph. So let's try one. Here's a graph of a car traveling from rest. The car has a mass of 1,500 kilograms. Just keep that in the back of your mind. It wants to know the final velocity of the car. Well, if we were to try to use some sort of formula, some kids go, okay, well, I know this formula. F delta T equals M delta V. So I can work with this formula right here. But look at the information you have. 1,500 kilograms, that's the mass. Velocity is what you're solving for. But consider force and time. Was force always 3012? Not consistently. Was the time always 578, or is that only the final time you had? So unfortunately, we can't really just plug in these numbers right here, but we do have a trick we can play. We can say, well, hang on, force times time can be achieved using a graph. I can calculate the force times time bit right here if I just make it equal to the area of this shape. The shape is not consistent. The amount of force that we underwent right here wasn't always 3012. It started and then got stronger and stronger as we went along. So if we were to do the formula 1/2 of base times height and find the area of this triangle, that would actually get me my force times change in time, which is really my momentum. So I'm going to take 1/2 of 3012, and I'm going to times it by 578. Why can't I just take 3012 and times by 578? That would imply that you were using this max force the entire time, and we weren't using the max force the entire time. We eased our way into it. So this is another way we can do that. 3012 times 578. My calculator spits out 8704.68. What does that even mean? Well, it's how much momentum it has. It's how much impact we gave it. It's how much impulse was given. Basically, this is how much momentum we have. And since my momentum is still equal to mass times velocity, if I divide both sides by mass, I should then be able to solve for the velocity. So if I take that number and divide by 1500, it's 5.80 if I did it right. Let's go with this thing limits me to 3 sig digs, it looks like. And since that's a velocity, that'd be meters per second. That might be something I need to talk with you about later, because it depends how much you remember graphs from last year, how well you did with graphs last year. Just a quick recap then again, just to remind you the concepts here. If you ever have a graph and the slope of the graph is useful, that's taking these two numbers and dividing them by each other. Then you find slope. If you ever have a graph and you want to multiply these numbers by each other, you have to use the shapes that you have. You might have a shape that's like a triangle for a while, then flat for a while, then back up. Hopefully, for those of you who were in my Physics 20 block, do you remember doing graphs like this? Okay, I can do a recap on it later if you'd like, but it is a skill we need you to have. Okay, so I think this is my last question. Why don't you guys give it a try? Without me adding anything to it, I'll give you guys 5 minutes. I'll throw on a Google timer. Let's see what you've learned over the course of the last, 45 minutes. So try it. Or sit there and do nothing, I guess. Hey, Google, give me a timer for 5 minutes.
Sure, 5 minutes. That starts now.
If anybody else wants a formula sheet, feel free to grab one. As a hint, the shape of the graph matters, right? Think about what we just did. How is the graph helpful to us? 54,000 kilometers per second. Did you remember to convert the grams into kilograms? Okay. Fair enough. Careful for that. So you're up by a factor of 1,000. No, it's not. It's faster than Earth moves through space, I think. Yeah.
So for the impulse, is it
Yep.
like this whole entire half?
Yeah,
or
will
the
be.
force of
Well, this whole half right here can be your force times time, but you'll have to do it with the area of the shape, so do the 1/2 mv squared, and you've now basically calculated this to be your impulse slash momentum slash oomph. And then once you've figured out that part, right, then if you divide by your mass, which is a given, then it should leave you with a velocity.
So
Does that make
if
sense?
you use this formula like the impulse.
Yeah, really, these two formulas are kind of the same thing as each other, if that makes sense, because this is impulse, and then since this is impulse and this is equal to that, then this is equal to that, so that's also impulse. Does that roundabout logic make sense? So, like, we're talking about everything we're talking about here today is kind of the same thing. It's all that oomph. Thousand. Milla is 1,000. Yeah, because impulse is momentum, which is, like, they're all the synonyms of each other, really. I'm sure somewhere deep down there's actually, like, somehow a difference between them, but, like, for our purposes, like, anything that has an impact is an impulse, so. I mean, based on what we have right here, like, I think we'd actually have to round it. But between here to here, the graph seems to limit us to 2, I would say. Because, like, when you went from here to here, you got, like, 1 exactly, right? But it's technically it's 1.0 based on the precision it was measured to. So I'd say 2 sig dig seems appropriate. Cool.
Would that be the impulse?
Hang on one sec here. Hey, Google, stop. So what did you do here? You took the mass given.
Oh, well, because I found that area of the triangle.
Okay. And then you... Okay, so the area of the triangle is your impulse. Yeah. And then once you have that impulse is really momentum.
Yeah.
So if momentum is mass times velocity, if you just divide by mass, you'll get velocity. Yeah. Okay. If you got far and got an answer, that's great. If not, let me just show you kind of my thought process as to how I'd solve this. First, you have to really have a good understanding of what impulse is. Okay. Impulse is momentum. It's impact, it's inertia, it's all the same thing. Impulse is like, I threw that one a little bit, and I threw that one really hard. That's impulse, right? The second one had more impulse. Does more impulse mean more force? Sometimes. But it also could have happened over a shorter period of time. There's 2 things that affect impulse. So impulse is not force. Yes, more force means more impulse. But if it happens over more or less time, that also affects impulse. Okay? Now, you can try to calculate impulse by finding momentum, mass times velocity. The problem is that all you have is a mass here. So hopefully you clued into what I was mentioning earlier. This graph is the clue. F times delta t is equal to momentum, which is equal to m times delta v. Like, they're all equal to each other. So if you can find the area of this triangle right here, you've found your momentum. You found your impulse. So just don't mess that part up. It's 1/2 of base times height. If you read the graph, this is not a consistent graph. It looks like the ball, there's no force to start with. Then the force gradually increases, and then it comes back down again. This is a golf ball being hit by a golf club. What I'm envisioning in my head is this: the guy is swinging. Right now there's no force, no force, no force, no force. As soon as the ball makes contact, you know how the golf club is going to start to flex and bend a little bit? It's flexing and bending and bending and bending up until a maximum force right here. And then as the golf shot gets released, right, then the force comes back down again as the ball and the club like disengage from each other. Here they're engaging with each other. Here they're disengaging from each other. So if I can then calculate the area of that, if you read this carefully, from right here to right here, looks like that's about 1 millisecond, which is 0.001 seconds. And the max height of this thing is 5,000. So to the answer to part A, should be able to do that in my head, you'd think. 5,000 times by a millisecond, divided by 2, I got 2.5. So the correct answer to part A would have been 2.5 impulse. What's the unit for an impulse, though? Kilograms meters per second, because it's really just momentum. I would say 2 sig digs. Based on what we read in the graph right here, I know this was 0.1 right here, and this was 1.1. But you remember talking about precision? They were both measured to the 10th. So when we subtract 1.1 from 1, I know the difference between these right here is 1. But like it should really be 1.0 because everything should remain measured to the 10th. So I would say 2 sig digs. Last step, if we want to find velocity, if we now know our impulse is our momentum, all we got to do is divide both sides by mass. So take 2.5 and divide it by 0.0459. With 2 sig digs, we're looking at 54. Did I do that right? 54 meters per second. Which seems about right. That's in the hundreds of kilometers an hour. That's reasonable for how fast a golf ball's coming off a club. So. Okay. I'm going to stop the video here, and then I'll ask you guys some questions here.